and two population proportions. And in all honesty, when I was a student, I remember something like this being taught to me. I also remember thinking to myself, okay, this is one of those like filler topics. Like it's not important. They just need to cover it. In like 10 minutes, this part of it'll be over, and then we'll get on to the real math. And then the real math, quote unquote, real math never happened. And I realized that I hadn't been paying attention for the last 10 minutes, and I was like, ah, crap. So, yeah, this is actually probably the most important part of the lesson because this is where you kind of get your grounding. The vocabulary. We have the null hypothesis, and we also have the alternative hypothesis. These are it's a one or the other kind of situation. All right. The null hypothesis, we use an H sub O as an abbreviation, right? And we use H sub A as an abbreviation for the alternative hypothesis, A being for alternative. The O, I say H sub O just because it's less syllables, but it's really H sub 0, and that's the numerical value of null, right? So null is 0. Anyway, the null hypothesis by definition is a statement being tested. All right, I gotta check. Also, some kind of preconceived notion, possibly, but we tend to think of it as the status quo. All right, so the long-standing belief, what is already in place, the common conception that people have of a situation. You know, basically, when you're running a hypothesis test or any kind of test, and we call it hypothesis testing, but if you think about the scientific method in any kind of science class, part of it is create a hypothesis and then collect some data, perform your experiment, collect some data, analyze your data, and then determine whether your hypothesis was true. Right? So all of that is a hypothesis test without the statistics component, but with more of an emphasis on the science component, with the experimentation part of it. The part where you're actually conducting the lab. You're working with the Bunsen burner, or the only one that I remember being actually interested by was refraction of light. With like prisms and stuff. So that I thought that was cool. I couldn't figure out or understand why any of it worked at the time, but I just thought it was cool. Because if you take a little piece of glass or crystal or something, put it in front of white light, and it breaks up into all the different colors from that, and like, wow, this is incredible. So that's what a raindrop does. That's wonderful. No idea why that works, but it's pretty powerful stuff. Yeah. So anyway, you'd go into one of those situations with, a wide variety of hypotheses. I usually have extra ones. I don't see any extra ones, so. Not in there. I usually put my extras in the drawer, but I share this room with some folks who are, we'll call it less than organized. You think you do? Yeah, because I don't have. Well, you got it so far. Phew, Jim. So, yeah, so where science has an emphasis on the experiment part of it, we have an emphasis on the analysis of the experiment. So what we would look at is the results after the experiment was carried out by somebody performing a lab or doing a research study, medical or otherwise. All right, so we have a preconceived notion going in of what the reality is, and we're trying to either reinforce that or disprove it. Right? So, a hypothesis could be, hey, I don't think gravity is 9.8, acceleration due to gravity is 9.8 meters per second squared. I think it's something else. And you know what? If it's related to the mass of the object, like gravity on Earth is 9.8 meters per second squared. What if Earth got bigger or smaller over time? Wouldn't that necessarily, or wouldn't it seem like it would make sense that gravity would be impacted in some way? So at some point down the line, that constant 9.8 may be different. So data would be collected and analyzed statistically to see if there is actually sufficient evidence to make a determination that the number is actually not the same. All right, so in the null hypothesis, we use an equal sign. So example, gravity, the acceleration due to gravity is 9.8 meters per second squared. All right. Then over time, somebody took some measurements, dropped some objects, determined how long it took for the object to hit the ground, kind of did some calculations, and determined that the value for gravity was something other than that. So they came up with some number more than 9.8, or less than 9. I'll go with less than 9.8. All right, so this would be the null hypothesis because it has an equal sign. This would be the alternative hypothesis because it has a less than sign. All right, so it's kind of weird, and I didn't really use notation there. I said gravity. I didn't say things about means or proportions or anything like that, like the title kind of suggests. I just used commonplace terms. Gravity is equal to 9.8. Gravity might be less than 9.8. All right. After I made my statements, I then designated whether it was a null or alternative hypothesis, because it's not like you decide. You don't get a choice in the matter, right? Oh, I want this to be my null. I want this to be my alternative. The one that involves the equal sign, the expression that involves the equal sign, is going to be your null hypothesis, and that is all there is to it. All right. If your equation inequality, well, it wouldn't be an equation if it doesn't have an equal sign. If I'll go with expression, it involves anything other than an equal sign, then it's an alternative. All right. So it may not be your alternative. It may be what you think is relevant, but it's what statistically we call the alternative hypothesis. It's very weird. One or the other, exactly. And that's a very, very, very important piece of information there, because it's telling us that there's no gray area. Once you eliminate one, you're going with the other. All right. Now, you may look at this and say, oh, wait a minute. They're not opposites. I got an equal sign, and I have a less than. All right. Well, you got to kind of think of it this way. You have a rope against the wall. All right. There's a little eye hook on the wall. You have a rope against the wall. You tie that rope to the back of a car. All right. You get in the car. Start driving. One of two things are going to happen. You're going to pull the eye hook. You're going to pull part of the wall out, right? Or something bad's going to happen to your car. All right. You're going to pull your bumper off, or you're just not going to be able to pull the eye hook out of the wall. All right. If you're able to pull the eye hook out of the wall, you have now removed equality. All right. So equality would be you're unable to budge. All right. So you have that car connected to the wall by the rope. No matter how hard you pull, you can't get that wall to budge. All right. That's equality. But if you are able to get the wall to budge, maybe you get the whole wall to move. Maybe you only get parts of it to knock down. Right? Maybe only the eye hook comes out. But if any part of it changes, then you have disproved equality. All right? So we don't have to go the other way. We don't have to have the wall collapse in on itself. It doesn't matter how the wall collapses. There just needs to be some change in the wall. Right? If that happens, then you've disproved equality, because the lone standing wall in its beautiful, pristine condition, I mean, look at that wall. It's a beautiful looking wall. I mean, as walls go, I'd give that a 7.2 out of 10. No, actually, that's disgusting. I mean, that wall's been here forever, yeah. Chalkboards. I mean, let's just put it this way. This chalkboard has been here since before chalkboards. Because look, they just built the border by hand. This is not like this is chalkboard material. This is scrap wood. They got slate and put it up here and then bordered it with scrap wood. This is like pre the invention of actual chalkboards. So, oh, maybe in that regard, it's like a fixture. It's an antique or something. I don't know. It's a fine work of craftsmanship. Anyway, so that's the idea. We don't have to show that it's more than 9.8. We're only testing negative 9.8, and whether it's less than 9.8. All right, and we'll see examples that are more relatable, because if you don't have a physics background, you're looking at 9.8, like, where the hell do you come up with that number? And that's fine. There's a lot of numbers. I mean, 120 over 80. A lot of people are like, where'd that ratio come from? So, but if you know where it came from, you know exactly what I'm talking about. So, alpha. So, funky little a, with a little extra tail, a little extra oomph on it. The Greek letter alpha stands for the significance level. That's actually a probability measure. It's a probability of rejecting the true null hypothesis. This is where it starts getting weird. All right. And actually, I could have sworn I changed this definition, or at least I offered it as a typo for like 7, maybe 8 previous classes. And it never got changed, which means nobody ever submitted it. Okay, well, it's the cutoff. For, or of, I'll say for. The probability of rejecting the true null hypothesis. Or kind of words to that effect. It's more of a benchmark. It's really more, I mean, just to paraphrase it a little bit, it's the desired probability. Because you never want to reject anything that's true. We haven't really talked about particular null and alternative hypothesis. I mean, I gave my little made-up example here, but that doesn't really count. But in a vacuum, just talking about the words themselves. Reject true. Well, that can't be a good thing, right? Do I want to reject something that's true? No, we want to keep things that are true. If it's true, I want it. I mean, unless it doesn't work to my advantage. That quote in Liar Liar. That is actually a great movie for understanding. I mean, they talk about the legal system and everything, but I think it's actually a great movie for understanding hypothesis testing, because like the concept of objections, overruled, sustained, that is null and alternative hypotheses. All right, the objection is your alternative hypothesis. Whether it's sustained or overruled will determine truth. Right? If you're sustaining your objection, you're going with the alternative. If your objection is overruled, then you're staying with the original statement. Okay, so that's pretty cool. But I remember that line. I mean, vaguely anyway. It was like, objection, and he was like, on what grounds? He said, because it's completely devastating to my case. And it was like, well, he had no evidence, but it was his rationale was like, it was not good for him. So That's the idea here with the alpha value. Right? Reject. Why? Because it's not good for us. Right? But that's not a good enough reason for us to say that something should be rejected. Well, I came in wanting to prove that gravity was more than 9.8, and this outcome just told me that I was wrong. I don't like this outcome, so it's bad. No, that's not it at all. If you reject something that is true, that is the definition of something that is bad. All right, whether you like it or not. We want this probability to be less than 9.8, less than 0.05. All right, because 0.05 corresponds to 5%. If something happens less than 5% of the time, that's not very frequent. Now, who decided on the 5%? Most people are all right just taking it as, a fact. 5% is the cutoff. Why? Because that's what we were told. 9.8 meters per second squared is the gravitational constant. Why? Because that's just how the world works. Cool. The best I could come up with is through research. Now, because I've looked at it mathematically, and so there's the research answer and the mathematics answer. Mathematics answer is better, but there's less clarity. The research answer was the person who came up with this concept was like, all right, so I need to cut off. I figure I screw up like 1 out of every 20 times. That's 5%. All right, so that's good enough. Go with 5%. Really? That's all there is to it? I don't know. If you're an A student, you kind of look at your grade. What makes you happiest? 100, obviously. Or better, right? You get a little Ken bonus action going on there, you're thrilled, right? But again, if you're an A student, like you're the 4.0 person, you're the person that most of us are jealous of. You're like, wait, you have a 4.0 average? What is it? Your first semester? No, it's not. I'm actually graduating college in like 2 months. So yeah, I've had a 4.0 for like 4 years. Yeah, I am very impressed. Yeah, like that. Like I didn't even have a 4.0. I had a 4.0 in math, but the other class was a crapshoot. So for the 4.0 student, like what's the minimum grade? Probably like you get something less than a 95, you're like, ooh, what did I do wrong? So you can look at it that way. But that's all anecdotal, really. You're just kind of considering your own life and other people's lives, and just perception, and perception is the mother of all. Yeah, really what it is the idea mathematically that there is statistically, and we'll actually show this. I'll show you some calculations later on. Statistically significantly a greater degree of error associated with 0.10 than there is 0.05. But not that much more error associated with 0.05 than 0.01. All right? If you use anything greater than 0.10 as your cutoff, then the amount of error in your results becomes so great to the point where the outcomes are so inconclusive that you cannot draw a meaningful conclusion from it. I guess that's the definition of inconclusive. But meaningful difference, but not deal breaker. Not much of a meaningful difference, but still a difference. Otherwise, we wouldn't distinguish the two from each other. But anything beyond these 3 values creates enough of an error to make your outcomes so wonky that your results would be all over the place. All right, basically, somebody could look at your information, draw one conclusion, and somebody else can look at the same exact information and draw the exact opposite conclusion. All right. That's what happens when your alpha values are too high. So what do? We use 0.05 if we are given the choice. Most of the time, we're not going to be given the choice. We'll be told in the problem. But if you are given the choice, go with the 0.05. Why 0.05? Well, it's the middle value. You got three possibilities. Go with the one in the middle. A better answer is, I'm using 0.05 in my answer key. Yeah, I'll change my answer key if you use 0.01 to check your work. But I'm not going to be happy. I mean, I'm not going to be upset either. It's just like, all right, well, let me just put this one in the pile of papers that I'll have to finish later because I don't have an answer key ready to go. So, bottom of the pile, you know? Yeah, it's in the grand scheme of things, it's a big deal. No, not at all. But that's rated quicker if, when you have a choice, you go with a 0.05. All right, and so these three blurbs here are basically everything I was saying, just without any pizzazz to it. Like that first line, most common because it assumes that error in an experiment can occur about 1 in 20 times. You know, it's like a blanket statement of fact, where anybody with half a brain looks at that and says, okay, cool, where the hell did you get that number from? Where did 1 out of 20 times come from? All right, so I get in the car 20 times, I'm going to get into an accident. 1 out of every 20 of those times? Well, that sucks. I gotta go to work 20 times every month. I'm gonna get into a car accident every month? I witnessed a car accident on Monday evening. It was a long day, but it was one of those. Yeah, we're all human, right? So you have these moments of weakness where you don't necessarily want to do the right thing, but you end up doing the right thing, right? So it's like you go by, the Salvation Army. Is it Salvation Army? Who's the one that, like, with the bell outside the supermarket? That's Salvation Army, right? So you're walking by, and he's ringing the bell, and you're like, all right, I'll get you next time. And then he starts singing Christmas carols at you, and you got a little 8-year-old boy there, and it's like, all right, I'll get you next time. Then he starts doing a medley of Christmas carols, and you're like, okay, I'm going to hell if I don't give you money right now, so let me walk back to you. So, like, by default, you kind of have to do the right thing. This one was a little bit more extreme because there was a 2-lane turn, 2-lane left. And diagram kind of helps. Here's a median. So we have our 2-lane left. So this one is the turn only. And this is the go straight or turn, right? You got choices there, right? So cars in this lane opts to turn, as was her right. Car in this lane opts to turn. All right, so that might surprise you. You might have thought I was going somewhere else with that. Opted to turn, but take it wide. Now, I think this is one of those accidents where maybe nobody was really at fault. I mean, yeah, he was at fault. Okay, but it wasn't like an egregious error. It wasn't like reckless driving. But it was one of those where I don't think he may have, like, consciously knew, but I don't think, like, he intuitively had an understanding that this car could also turn. So when he made the turn, I think he thought he had a choice of 2 lanes to go into. Right, so he made the turn and he broadsided her. Right in it. I mean, not too hard though. But actually, it was kind of like worse. It was more like bumper cars, where there was the impact and then the push. So he's like continuing to drive because he like got pedals mixed up and things like that. And so You know, it wasn't like injurious. You know, nobody got hurt.
Have to use that left lane. Let's say 100% sure, you know?
Yeah, I always go for the left lane because I'm like, listen, I can take the hard turn, and I'm usually going to be okay. But then oftentimes I'll see people go from this lane and be like, yeah, but I need to get left, and they'll almost take me out. So you gotta drive defensively no matter what.
But sometimes it just goes straight. You're trying to turn.
Yeah, that's what like when I started telling the story, I figured most people were thinking that this guy was gonna go book it, but and I've seen that happen too. So I'm the car behind this car, and I'm watching the whole thing unfold. So so I'm a witness, right? Yeah. But I watch other people do stupid things all the time. It's really, I guess it's my lot in life. I'm like the witness. So I'm sitting there watching this whole thing unfold, and the two cars are like in a T formation right in front of me, blocking my path. So my response was like, it, or at least my inclination was, all right, well, let's see if I can scoot around this disaster and go pick up my son from school. And then I was like, ah, crap, I'm going to be stuck here for the next 20 minutes. I can't get past them. To, oh, I kind of witnessed that whole thing happening.
Don't you hate it when they just stop in the middle of the road instead of like pulling to the side?
Yeah, I mean, that's what happened there. And so that was my suggestion, where I was like, you pull off over there, you pull off over there. Turned out,
Insurance purposes, don't stay like that, no?
depends. Some of them are, like, if it's a fender bender,
Somebody gets hurt only. No, but you can claim it.
right, but if there are witnesses, then it's fine. In fact, there's signs that on the George Washington Bridge that say if it's only a fender bender, get off the bridge. They're like, it's not gonna, like, regardless of what you think about insurance, that's not how insurance works. It's they have different categories. So I got my bearings. I realized I was going to be there for a little while. Once I realized that I couldn't just like peace out, and I realized that one of my colleagues from the high school was the lady driving the car that got hit, like in the math department. Like I share a classroom with her. So then I was like, oh, yeah. I was like, we communicate sometimes. We say good morning and things. So I was like, oh, I really can't go. Hey, all kidding aside, I was actually invested and motivated to stay at that point, because it was like three guys in the other car, and she was alone. And not to say that she couldn't handle herself. She's a feisty gal, but like it was like, listen, anytime you have three against one, it doesn't matter what gender is. It's like people would start browbeating other people. One of the guys came up to me and said, "Hey, you saw that, right? She jumped the turn, right? Right? A lot of rights, like, right? That's what happened, right?" I'm like, and like my less than professional verbiage comes out. You start to get an understanding of how I normally speak. Get an understand. I'm like, "Yo, bro, I don't know what you're talking about, dude." So. So like the light turned green and she like followed the rules. And so what you did was like not that. You messed up, man. And so I don't know what you want, but don't worry, you don't get arrested for that. It's fine. Like you just tell the cops, I made a mistake. It'll be all right. And he's like, no, it really happened like this. I'm like, no, actually it didn't. I watched the whole thing. I was there. It was a good show. I recommend you follow the rules next time. But so that was my Monday evening.
Was this a White Plains?
No, this is in Cross River, so like half an hour north. No, White Plains, it would have been like a fatality. It would have been like traffic jam for 40 miles in every direction. Like, oh my God. And also, it wouldn't have been a story, because I would have been like, oh, you witnessed an accident in White Plains, huh? Oh, okay, join the club, pal. Like, like, what are we talking about here?
There's cops everywhere, so it take a long time to get this.
Yeah. In this one, it took them about 45 minutes to get there, because I mean it was right over the 684 overpass, and you just look down to 684 and see it backed up, and you could see cop car after cop car with their lights on driving up the shoulder, because whatever accident that I just witnessed, it wasn't as nearly as bad as whatever they were going to, so we were kind of on the back burner. But you know, it is what it is. People drive like schmoes for some reason, especially in parking lots for some reason. I don't know why. Oh, it's like, listen, just back up. Yeah, I mean, I don't understand. I mean, just make a choice. That's all. That's all I ever ask. You know, quick drop off. That happens. Now just drive away. 3 choices, all of that was to say go with the 0.05. Obviously, I think the test becomes stronger as alpha goes closer and closer to 0, and that's because if alpha represents the cutoff value for rejecting something that's true, so the cutoff probability for something that's bad, the smaller you make that probability, the better off things are going to be. All right, but if I'm telling you statistically that there isn't much of a difference when in certain situations, in some situations, depending on the units, depending on the nature of things, it may make a difference, but generally speaking, it's not going to make much of a difference. Any of these 3 will work. But the thing is, now human perception comes into play. Because if I tell you that the probability of something bad happening is 0.05, then the corresponding probability of something good happening is 0.95. If I tell you the probability of something bad happening is 0.01, then the probability of something good happening is 0.99. So if I tell you that you got a 99 on a test versus a 95 on the test, the 99 sounds better. A lot better. It isn't a lot better, but it sounds a lot better. So if I tell you that I am 99% confident that whatever, 99% confident that you're going to get an A on the next test, you're like, wow, that's great. If I say you're 95%, I'm 95% confident you're going to get an A on the next test, you're like, okay, that's good. 1 out of 5%. Like, what you think less of me clearly because you didn't say 99. I mean, people talk like that all the time. They say, oh, like, I'm 99.9% sure of this, that, or the other thing, right? Nobody says I'm 95% sure. I'm 87.5% sure, except for me. But, yeah, 99 just sounds so much better. So you'll see that if you read the fine print for those medical commercials where they're trying to push some allergy medicine that'll kill you. Yeah, it's like, this medicine is great if you have allergies. But if you have depression, it's going to make that a lot worse to the point where you may want to kill yourself. So, you know, be careful if you take this. I'm like, whoa, what do you mean be careful if I take it? How about don't take it, I'll just sneeze. What's wrong with you? So,
also with the bipolar medication, a lot of side effects.
Right. Yeah, and they say it so fast, but it's like, oh, your heart could stop working. Like,
I have a bipolar son, so since he was 12, so many different medications, all these effects.
it's always, yeah. You find one that works too, then it's like the side effect is what does you in. This is an important component here. Significance of the hypothesis test does not always mean there's a strong effect, only if there's strong evidence of some effect of some imposed treatment. All right. So going back to my gravity example. So this is the difference between getting something right on a test and understanding why you got it right. All right. My gravity example. If I disprove that gravity is equal to 9.8 meters per second squared, and so I have proved that it's less than 9.8 meters per second squared, that is really addressing this idea. It's not telling us in what way it's less than 9.8 meters per second squared. It's just telling us that it's simply less than 9.8. It could be 9.7. Gravity could be 9.65. Gravity could also be 1.28. Like, it could be drastically different. It could be a little bit different. It could be somewhere in the middle. It could be 9.79. That would technically prove a difference from 9.8. Right? So this whole process doesn't show us what kind of difference it is, just that there is a difference. All right. That's very important. Hey, I'd like to think that I hope anyway that I do a decent job of emphasizing what is important, but I find myself saying, this is important, this is important. I feel like I'm saying it about everything, but basically everything that I circled or highlighted on this page, except for that, because well, it's important because it's a typo and you can get bonus, but anything that I annotated here, it's important stuff, at least for understanding. Power. The term power, I don't think is important. All right, in terms of understanding things. But the concept, I think, is important. Okay, so what it's called, I don't know that anybody has ever really needed to know that word specifically. And in fact, when you really start getting a true understanding of this material, you know, you see the irrelevance of it. The easier it is to reject the null hypothesis, the more power a test has. Okay, so, okay. If I want to increase the power of a test, increase alpha, that makes it easier to reject the null. Okay? That's not meaningful yet. We'll get to that in a few minutes. Increase the sample size, thus decreasing sigma. I'm not a big... I don't like the word thus. It just sounds stupid. I know there's a place for it, but there's a convention, like you use thus under certain circumstances. I don't think I've ever successfully used it correctly on my own. I copied this right out of a textbook. I will take a rephrasing. Thus it must be. I'll take a rephrasing of any sentence fragment, whatever, in my notes that involves the word thus for something that doesn't, and I'll count that as a typo bonus, even if you're at the max. That's how I find that. Right? So therefore probably works. Anyway, so yeah, if you increase the sample size, your variation decreases, and therefore your test becomes more powerful. Type 1 and type 2 errors. Another thing where the actual type 1 and 2. All right, well, why do we need to distinguish them? An error is an error, right? Somebody somewhere along the way thought that it was important. Type 1 error is rejecting a true null. That's like the worst thing that you can do. So, I mean, when you think about it, okay, if you're gonna create a hierarchy of errors, then the first one that you indicate is probably gonna be the worst one. Right? That's the one that you're on the lookout for the most. All right. This is terrible. Terrible apparently has 2 R's. Terrible. All right, rejecting a true null is terrible. Accepting a false null is bad. All right, neither of them are good, but one of them is worse than the other. All right, because if a null hypothesis is a long-standing belief or status quo, basically, potentially, something that society could be built around. If I'm mistakenly rejecting that, that's terrible. Our entire society comes crashing down because I got rid of a long-standing rule or belief and I was wrong. Ugh. Accepting a false null, that's still bad. You know, because if you're talking about a long-standing rule or belief that should be dismissed, but statistically we're unable to prove that it should be dismissed, and the reason we're unable to prove it is because we made a mistake somewhere. Well, that doesn't sound good either. And you could think about instances throughout American history alone where there was a long-standing rule or belief that was bad, that, yeah, it would have been nice, more than nice, to get rid of that long-standing rule or belief. Um, but yeah, without going too much into that kind of stuff, we'll just leave it. Although prohibition, maybe, to keep it on the lighter side, might be an example that would fit both categories. Right? So the institution of prohibition might be a type 1 error. I don't know what people's beliefs are, that sort of thing. But let's say that, well, there is no prohibition now, so at some point people decided that there was more money in allowing people to drink alcohol. I mean, because that's really what it is, right? It has nothing to do with health. If it had to do with health, then that wouldn't be allowed. Caffeine wouldn't be allowed. Tobacco wouldn't be allowed. Income tax wouldn't be allowed. Because that messes up my blood pressure more than anything, I think. And healthcare in the future. So anyway, so the long-standing rule that was dismissed would be, hey, it's okay to drink alcohol. Right? But we got rid of that, instituted prohibition. Type 1 error. Right? Accepting the false null. Right? That would be continuing to keep prohibition. Like a year later they say, all right, well, I think we should look at this prohibition thing again because the people seem to be very upset about it. Maybe we should get rid of it. They ran their data analysis and they said, you know what? Nah. Turns out that the people still like prohibition, so we're going to continue to use it. Accepted a false null hypothesis. We also think of alpha as the probability of making a type 1 error because alpha is the probability of rejecting a true null hypothesis. A type 1 error is rejecting a true null hypothesis. So alpha is the probability of making a type 1 error. All right. Obviously.